Welcome. In this video, we will take a look at lesson 3.6, which is looking at area between two curves and average value of a function. So our objectives for this lesson are to consider finding the area in between or of a shape using integration, and usually that will come again in the form of the area between two curves or two functions in general. And then we have the objective of considering finding the average value of a function using an integration technique. So let's go ahead and jump into the first topic of the area between two curves. So when we consider just graphically for a moment the area in between two curves, the area that we're finding is going to be the area that's below the top curve and the area that is above or over the lower curve. So all that area in between, in this case, all that green shaded area is what we're after when we're looking at the area in between f and g. So by definition, we can find this area by taking the integral or of the f of x function from a to b, wherever those endpoints might be. That would give us the area all underneath this blue curve, f of x. But we don't want to capture any more area than we have to. And so we don't want to capture that area that is trapped below the red function or the g of x function. So I'd like to subtract that area that's below my g of x function. So this becomes just really a difference of integrals where we have the upper function minus the lower function in our integral from a to b. And those would be our endpoints of that integral. So we're going to go ahead and now consider taking a look at a few of these enclosed regions. So the first one says we want to determine the area of the region enclosed by the parabola y equals 2x squared plus 4 and the line y equals 4x plus 20. Now, when we consider this integral, again, we're going to want to set up an integral with bounds a and b, where we again have the upper function minus the lower function dx, and that will give us again the area in between those two curves or lines. So the one thing is going to be, first, can we find those bounds a and b? They don't actually give us bounds here, but we know it's going to be enclosed between this parabola and line. So if we were to just consider even the shape of these two functions and where they would sit on the plane, the first function is that parabola that looks like an intercept of 4. So let's just say that's at 4. We're going to have a kind of a parabola function coming up like that. And then we have a line that has an intercept of 20 and is again a positive slope. So when I jot this in, again, we can maybe even bring this up, increase that a little bit. If I just look at those shapes, there's going to be maybe 20 is all the way up here somewhere, and we have a positive slope that's going to be created here. So it looks like, just based on kind of a sketch of these two functions, that we can actually determine that the upper function is going to be our line, and that lower function would be the parabola in this case, because we're looking at, well, the area that's going to be enclosed, everything in between here, well, the line is always on the top side of that area, and then the blue function always lives right below or is the lower bound on that area created. So that is a good help to us. And we can actually confirm these shapes if we want to, and we could take a look at a graph. And these are kind of the two functions, and it looks pretty much what we had there in just a quick sketch. Again, that line encloses the upper portion of our trapped area here, and the red function, the parabola, would have the underside of that trapped area. Now, the bounds on this will be these values that we intersect. So the values that intersect both on the left and the right side will be those bounds of integration, A and B. So we'd like to go out and see, well, where do these two values actually intersect each other? So let's go back to our work here and consider how we would set up our bounds. And I'll do this on the right side here. So the bounds we can find by just considering setting these two functions equal to each other and seeing where they actually intersect. It's very similar to a system of equations where we're finding where maybe two linear functions would line up. We could do this with a parabola and a line as well. So we're going to set these two functions equal to each other. Maybe I'll do this on the right. Yeah, we'll do it right here. 2x squared plus 4. And then we'll set that equal to the second, the line 4x plus 20. And it looks like this would be considered as a quadratic. So let's see if we can subtract everything over to the right. We'd have 2x squared, we'll subtract a 4x, and then subtracting 20 over to both sides would give us negative 16 equal to 0. And it looks like we can do a little bit of factoring here to get started. If we factor out a 2, we get negative 2x and negative 8 set equal to 0. And I believe this does factor cleanly for us, so we do have some bounds we can grab. If we factor this into 2, we would have the product that gives us negative 8, or those factors that give us negative 8 and add to negative 2 would have to be negative 4 times positive 2. So we could have x minus 4 and x plus 2. So these two solutions that we're going to get are going to be x equals positive 4 and x equals negative 2. So that left bound, again here, is going to be that negative 2 value, and wherever we cross over here on the right side, it's kind of off our little sketch here, but that would be at x equals 4. So again, they're not a perfect picture, but I think at least based on the picture that we kind of created in our side here, I think those values seem pretty logical. So let's go ahead and set this up now. We know the upper and the lower function, and we know our bounds. And so let's go ahead and consider finding the area through integration. So we're going to have the integral of the bounds from negative 2 to 4. The upper function, again, is our line. So we'll write that one first. And then we'll subtract our parabola, 2x squared plus 4 dx. All right. And doing a little bit of distribution to get started here, we can keep this, again, as a definite integral. We'll distribute the negative sign here to get negative 2x squared, negative 4, and then we can consider adding some like terms here. I'm going to go and use our negative 2x squared and put that in front. We'll have a plus 4x, and then the 20 and the negative 4 here can add to get positive 16. So we'll notice that this is the exact, really opposite as what we found when we set these equal to 0. And that's the integral dx. Now we get to just consider an antiderivative of this function, and then we'll consider the evaluation. So antiderivative first, we can say this will be negative 2x cubed divided by 3. 4x becomes just 4x quantity squared over 2. And then plus, we'll have 16 times. X is right now really to the 0 power, so we'll just add x to the first power. And since this is a definite integral, we can just consider evaluating this. We don't have to have that constant plus c in here. So now we can just go ahead and consider doing our evaluation from negative 2 to 4. All right, so let's go ahead and evaluate this. First off, we could just do some reducing here. This is really just 2x squared in the second term. That'll help us whittle that down just a little bit. So let's start with the evaluation again at 4. So we'll take this evaluation at 4, then we'll have negative 2 times 4 cubed over 3. We'll have plus 2 times 4 squared. And then finally plus 16 times 4. We'll take that as a bracket. So that's one evaluation. We're going to, again, then subtract this to the evaluation of that antiderivative at negative 2. So we'll have the negative 2 starting at the beginning again, times negative 2 quantity cubed, divide by 3. We'll have plus 2 times negative 2 squared. And then finally plus 16 times negative 2. So with all of those pieces there, we can go ahead and evaluate that. If you do evaluate this correctly in your calculator, we should get a value of 72. So I encourage you guys to jot that. If you need to pause the video, you can double check that result in your calculator. Make sure that you can evaluate a function of that type. So that should come out to an even 72 units of area here. So this again gives me the area trapped between the two curves or functions. Perfect. All right. So that is our first example. Let's go ahead and take a look at a second one where the upper and lower functions are not always the same throughout the problem. So we want to determine the area between the curves f of x is equal to the square root of x and g of x is equal to just the function x on the interval 0 to 4. So let's go ahead and consider just, again, doing a small sketch of these two functions. They're pretty small, so we should have a pretty good idea of kind of what the shape of our square root function and just the x function itself is. So let's start with just the g of x function. We'll do that one in red. So g of x itself here is going to be just the y equals x. So that means that my output and my input are the same for all x or for the whole domain of the function, which is all real numbers. So we'll just have a straight line both directions there. So that's our g of x is equal to x. And then our square root function, let's go ahead and do that in a different color. We'll do that in blue. So this is our f of x function. Well, the square root function is going to be an increasing function over time, but it's more of a gradual increase. It looks like kind of a slow increasing arc here. As x increases, the function does increase, but it doesn't increase as fast as just y equals x. So specifically, it'll start at 0, and then we'll consider x equals 1. This is an important point for us on this function. Well, the square root of 1 is 1, just like it is for the x term. So those two are going to be the same. And then throughout the whole function, it will just kind of decrease or increase there gradually. So we're going to have kind of the increase gradually to the right for that square root function. And just to give an idea here, at 4, maybe we should have this increase just a little bit more. We'll try this. Maybe a little bit like that. By the time we get to our end of our interval, which is x equals 4, well, the square root function should output a value of 2. Because the square root of 4 is going to be 2. So just maybe some helpful points there to plot for us. Okay, so let's go ahead and now consider what would our integral look like for the area in between these two curves. So notice that in between this interval from 0 to 4, I actually have these two functions crossing at x equals 1. They're going to be both equal to 1. So this is the height of 1 we'll have at the input value of 1. So this means that we're going to really be solving for two different areas here. One's going to be the area in between this little sliver from 0 to 1. And then we'll also want to consider the area that's created between these two functions if we were to extend this from 1 to 4. So if I can extend this function all the way through, we're also going to be grabbing this area in between, but the second portion, we change what's the upper and lower function here. So let's go ahead and maybe label these two parts A and B. So let's call this area here A, and then this larger area we'll call the area B. So if I was to set up the integral that would solve for this area A, well, we could set this up as the integral from, looks like from 0 to 1 would be our bounds. Our upper function for this would be the square root function. So we could say the upper function is the square root function. Subtract the integral of our lower function, which is just going to be x for us, dx. So we have an integral there to solve. We'll also be able to set up another integral that would be the integral for the B area. So we can do that for the B area. This would be the integral now from 1 to 4. That's the rest of our interval. So 1 to 4. But now our functions are actually reversed. My upper function is now the x function. My lower function is my x, or the root of x function, dx. Now, if I was to, again, add these two components, the A area and then the B area that we're doing in the purple, we should be able to get the actual total area trapped between these two curves. Okay. So let's go ahead and we will walk through both of these. They're going to have very similar antiderivatives because they have the same terms involved. So let's start with the integral for the first part. We're going to have really x raised to the 1/2 here for that square root. So we can still use our power rule for this integral. We'll have x raised to the 3/2 power, and then divide by 3/2 minus x squared divided by 2. If we clean this up just a little bit, I think we can work towards evaluating this. Dividing by 3/2 would be the same thing as multiplying by the reciprocal, and that would be 2/3. We'll have x to the 3/2, and then minus x squared over 2. And again here, we're going to evaluate this from 0 to 1 for that first integral. So first, let's go ahead and evaluate this at 1. We'll have 2/3 times 1 to the 3/2 is just 1, minus 1 squared is just going to be 1 divided by 2 will be 2/3 minus 1/2. And then if I evaluate at 0 next, we'll just have 2/3 times 0, and then minus 0 over 2, which is again still 0. So when you put these two fractions together, 2/3 minus 1/2, you end up just getting 1/6 unit of area there for that solution. 1/6. So that would be kind of a tiny area there between 0 and 1. Now let's go ahead and shift gears to the B area. Again, this should have the same antiderivative, but just written in reverse. So we have x squared over 2 for x, minus, we'll have the 2/3 x to the 3/2 left over. So it's again the same as the function we had from before, but those terms are now just reversed. This we're going to be evaluating from now 1 to 4. So let's go ahead and evaluate here. We'll first again evaluate here at 4. We'll have 4 squared divided by 2 minus 2/3 times 4 raised to the 3/2. And then we will subtract the evaluation at 1. So that would be our 1/2, 1 squared over 2. And then we'll have negative 2/3 times 1 to the 3/2, which is, again, just going to be 1. So we can multiply that by 1. Now, just working out this, I think we can quickly do this maybe in just by hand real quick. We've got 4 squared over 2 would be giving us 8. If I take the 2/3 and I consider 4 raised to the 3/2, well, this value, 4 raised to the 3/2, is another way of saying 4, take the square root for that half, and then raise to the 3rd power. So square root of 2 or 4 would just give us 2 raised to the 3rd power, would give us 8 here. Okay, so we're going to just have, in other words, this value as 8. And so 2 times 8 is going to give us negative 16 over 3 for that result. Minus, we already did the 1/2 minus 2/3. This would, you can keep this as is for now if you'd like. So 1/2 minus 2/3 here. So if we put these values together with kind of the like denominators here, we're going to have here 8 and minus 1/2, and then we'll have a plus 2/3 when we're done. So we'll have 8 plus, oops, we'll do the minus 1/2. We have minus 16 over 3, and then we'll have plus 2 over 3. So a couple of these have common denominators here. And it looks like we'll have 8 minus 1/2, or we can multiply that by a 2 over 2 to get 16 divided by 2. So we have 16 divided by 2 minus 1/2. Then we'll have negative 16 over 3 plus 2/3. We'll have 15 over 2 for combining these two values. And then negative 16 over 3 plus 2 over 3 will just give us negative 14 over 3. And if we work to get a common denominator here, I think we can do that with a common denominator of 6. So we'll have to do multiply by 3 over 3, and then 2 over 2 for the last bit. So this becomes, looks like 45 divided by 6, and minus 28 divided by 6. And that'll give us a final result here of, looks like 17 over 6. 17 over 6. So we do get the exact value there, 17 over 6. And those two values, again, are not the final result, because we do want to add those two components, the A area that we got from the first part, and our B area, which is the 17 over 6. And if we add A plus B, or 1/3, or 1/6 plus 17 over 6, we will just get a total of plus 3, or 3 positive units of area total by adding those two components. So we've got to have both of those components to be correct there. So there's again a question that the upper and lower functions do change throughout the problem, so we'll have to watch out for those in the future as well. Now, the last one we'll also consider maybe a graph to get started. So let's drop down to our last example for areas between two curves. So we want to determine the area of the region bounded by y equals x times e to the negative x squared. And then we will have the integral, or the function y is equal to x plus 1 and x equals 2 and the y-axis. So a lot of regions here. So let's go ahead and again consider the integral we're going to want to consider is, again, x equals 2 is going to be one of our bounds, x equals 2. And then with the y-axis, this is another way of saying just x equals 0. So we're really going to consider x equals 0 to x equals 2. So that's really going to be our bounds on this function. So 0 to 2 We'll start our integral. Now we just need to figure out, well, what's going to be the upper and the lower function here? Is it going to be our exponential function or that linear function? So this one might be a good one to go ahead and try graphing, either in your calculator, or you can try Desmos if you're just working this out. So let me show that. We'll take a look at Desmos for this one. Here's our exponential function and our linear function from x equals 2 to 0. We'll get in a frame where we can see this. And it looks like the upper function here is going to be in red. That's the linear function. And my lower function is the x e to the negative x squared. So it's kind of a curved function that goes along the x-axis there. So this is the region that we are taking a look at, and we could even maybe make an educated guess of how large this final value should be, just based on kind of what area we take up here. So if you notice here, we've got kind of a triangular shape kind of going. If we were to cut horizontally here at y equals 1, and that would be a looks like a almost 2 by 2 triangle, or have 2 units of area there, and then we'll have plus some other area here. So we can imagine this is going to be somewhere between like 2 and 4 maybe, would be an educated guess for kind of the area between those two curves and the line x equals 0 and x equals 2. So just before we get started, it might be good for us to have kind of that mindset so that when we get a result, we can kind of logically check that with our graph. So let's go ahead and try this out and see what we're going to get. Again, the linear function here is going to be our upper function, so we'll start with that one. So our upper function, x plus 1, is going to be the first, and then we'll subtract our lower function, which is the xe to the negative x squared dx. Now, as I write this, it looks like one of these functions, again, is going to need some extra treatment in terms of the integral itself. It's not going to be just a really straightforward integral. We might need to use one of the techniques from our last chapter. And so it might be helpful here to kind of, again, pull these two integrals apart and look at them separately. So that's what I'll do here. And I'll go ahead and pull this and say we're finding the integral first of x plus 1 from 0 to 2 dx would be part of it. And then we're going to subtract, keep that negative sign inside, and then we'll have the integral from 0 to 2 of x e to the negative x squared, and then dx. So we'll try to do this in those two parts. So let's start with the smaller one, just x plus 1. So x plus 1, we can have an antiderivative of x squared over 2 plus x, and then we'll evaluate this from 0 to 2. So when I evaluate this portion here from 0 to 2, I think I can find a value pretty quickly for this. Evaluating at 2 will give us 2 squared over 2 plus 2, and then we'll have evaluation at 0 to be just 0 over 2 plus another 0. That's not going to contribute anything to that integral. So for this one, looks like 2 squared over 2 is 2, plus another 2 would just give us 4. So that portion of the integral there is just going to be 4. So now we're just going to go ahead and kind of focus on this last part of the integral with the xe raised to the negative x squared. Now, notice that this integral is probably going to take, again, one of our special techniques. Let's consider maybe what technique might be helpful here. So if I was to consider, let's just say, u substitution here, I could consider changing this to u variable by substituting u in for this x squared value. This x squared. I think that might be our best bet here. So let's go ahead and substitute here. Now I'll actually substitute for negative x squared. That'll be okay. And du for that, the derivative with respect to x there, is going to be negative 2x dx. There we go. Negative 2x dx. Okay, so looks like I have a good amount of the components here. Again, remember that this has a negative sign out front, and that'll be helpful for us later on too. So I'd like to, again, account for all of the terms in this integral, if I can. So to do that, I've already got that exponent carried with the negative x squared. I can rearrange my du function here and make this du divided by negative 2, which is going to be equal to x dx. So again, that would take care of that dx term and the x there. I think that would be an appropriate way to consider that. One other thing is I can consider my bounds. So when x is equal to 2, we want to consider, well, what's my bound in u? So I can just change over to the bounds of u and then evaluate that. So when x is equal to 2, it looks like here we'll have u is equal to negative 2 squared, which will give us negative 4. And then when x is equal to 0, well, it looks like negative 0 squared is also going to give us u is equal to 0. So my new bounds here are going from 0 to negative 4. So let's go ahead and rewrite this. Again, we have the minus outside here, and then we'll have the rewriting of the bounds. So instead of 2, we'll put negative 4, and then at 0, we'll still remain at 0. My e raised to the negative x squared is just going to be e to the u power, because that's taken for the exponent. And then the x dx portions that are remaining, again, become that du times negative 1/2. So for this, I can bring that negative 1/2 out in front, and then we'll have du written there. And that totally changes, or it interchanges my integral of x to an integral of u. Now we can say that the integral of e to the u itself, well, that one is just going to be e to the u. There's no change in the exponential function. So when we're done, we'll actually have here a double negative, so we'll be adding these components now. So we'll have a sum adding those two components. And this will have our just integral of 1/2 times e to the u, and we're now evaluating from negative 4 to 0, or 0 to negative 4 here. All right, and let's go ahead and evaluate this function here to finish it up. So we'll have 1/2, and then we'll have e raised to the negative 4 first, and then subtract, we'll have 1/2 e raised to the 0, and e raised to the 0 is for us just going to be 1, so this term just goes to 1, times 1/2. So if I put all of this together, let's go ahead and again consider adding now my two components again, because this turned to a plus. So we've got 4 for that first part, and then we'll have plus 1/2 e raised to the -4, and then minus, we'll just have 1/2 on the end there, 1/2 times 1. And if you put this into your calculator, this will come out to approximately 3.51 as that area in between the two curves, 3.51. Which I think from our previous discussion about the picture or the graph of this function, it looks like that's a pretty good estimate for that area. It should be right in between 2 and 4 units of area in between. All right, next we'll take a look at the average value of a function. Let's start by taking a look at the definition for the average value of a function. So the average value of a function, we'll call f of x, over an interval a to b is given by the integral from a to b of f of x dx times, here a constant, 1 over b minus a, which is the length of the interval. So let's go ahead and now consider how we might get to that equation. So we can imagine that the area under f of x that we have here is a container filled with liquid. It could be much more efficient to ship rectangular containers that have that same base area when we go to ship this. And so we can consider, what if that level of liquid evens out here, and we get some height h that kind of averages, again, the height of that container in part B. So the area of this rectangle that's created when our liquids kind of level out would be considered as, well, it's the height, h, times the b minus a length of that base, would be the area of that rectangle there. So we know that that same area could be represented with our integral. So that same area in yellow is represented by the integral from b to a of the f of x dx function. So in other words, we get the relationship that our integral from a to b of the function is equal to that area of h times b minus a. And so this gives us the opportunity to solve for, well, what's that average value or that height of that function, the y value, and it ends up being the integral itself divided by that constant, which happens to be b minus a, which is the length of our interval. And this is what gives us the average value of the function, or it's the average y value of our function. So this gives us the average value, or again, this is an average y value of our function. And there's our kind of visual proof to get there. This also is connected to what we call the mean value theorem. We won't work with this too much in our class, but it is a valuable theorem from calculus that I'd like to mention at least. It says if f of x is a continuous function over that same interval a to b, then there exists a value little c in that interval a to b such that the integral itself, integral from a to b of f of x dx, is equal to the functional value f of c times b minus a. Now that capital F or the f of c, that value, that is really going to be the functional value that's describing that average value. So if you wanted to kind of notate that picture, that f of c is going to be that average value there, f of c. Or c is the value that, the input value where we reach that average. So that is always true for us. So let's go ahead and find our average value here for a given function over the interval 1 to 4 here. So I'd like to, again, get my average value. So let's go ahead and set this up. We're going to have the average value. I'll just say average value. The AV, average value, is going to be equal to the 1 divided by b minus a. And for us, we have the interval from a to b of 1 to 4. So we have 4 minus 1 is the size of our interval. We want the integral from 1 to 4 of our function. In this case, it's x squared plus 3x plus 2 dx. We're again setting up that same average value equation, 1 divided by b minus a, and then the integral from a to b of our function. So let's go ahead and start that integration process. Right off the bat, we can find that that interval for our average value is just going to be over 3 units. And then we can consider, well, what's the antiderivative of our function? So we can say that that antiderivative will be x cubed over 3 plus 3 times x squared over 2, and then plus that final value will be 2 times x. And we would like to evaluate this over the interval from 1 to 4. So we'll go ahead and jot down the results from this. We'll have the 1/3 power times the evaluation. Let's go first for the evaluation for 4. Let me just do this in all the same color. So starting with the evaluation at 4, we're going to get the 1/3 times 4 cubed divided by 3 plus 3 times 4 squared divided by 2, and then plus 2 times 4. We'll subtract this from the evaluation at 1. So we still have that 1/3 times. We'll have 1 cubed over 3, which is just going to be 1/3, plus 3 halves times 1 squared, which is, again, still 1, and then plus 2 times 1. So each of those are at the valuation at 1. And if we go to evaluate this all the way through, we should find that this is equal to 16.5 as our average y value on that interval. So the average value of the function would be 16.5. Let's go ahead and consider an application through average value here. This says that during a 9-hour workday, the production rate at time t, hours after the start of the shift, was given by the function r of t equals 5 plus square root of t cars per hour. So we want to find the average hourly production rate. Okay. So if we want to consider, again, this could be kind of a car manufacturing plant here, if we're producing cars per hour, if this is our rate function, we want to integrate that rate to consider how many total cars are passing through in our time. If we want to go with our average hourly production level over that 9-hour period. So let's go ahead and set this up for our F average. I'll use that same notation. F average is going to be equal to, again, over that interval, our A is going to just be 0, and B we'll call just as 9 if we consider that as a 9-hour workday. So we'll have the integral 1 over 9 minus 0, and then the integral from 0 to 9 of our function 5 plus the square root of t dt. We'll take this integral with respect to time. So if I want to find, again, that average production rate, we'll have the 1 over 9, and then we'll take our integral, 5 plus t, square root of t. We'll have 5t as the first antiderivative, and then plus, this will be t. This begins with as a 1/2, so we get 3/2, and then divide by 3/2 would be the same as multiplying by 2/3. So let's go ahead and just flip that around and consider this as 2/3 times t raised to the 3/2. And then we'll evaluate this function from 9 to 0. So we'll have, looks like 1/9 on the outside, 5 times 9, and then plus 2 times, this will be the square root of 9 itself, quantity cubed, when we put that into the 3/2 power, divided by 3. That would be our evaluation at 9. When I look at that evaluation at 0 to subtract, notice that if t is equal to 0, none of this actually survives, and we'll all just have zeros. So we just have kind of subtracting by a big 0 on the end of that evaluation. So let's just take a look at what remains here. Certainly we'll have a 1/9 times 5 and 9 give us 45. And then we'll have a square root of 9, which gives me just a 3. And so that would be 3 cubed times 2, and then divided by 3. So we'll have plus 3 cubed times 2 as 54 divided by 3, which does go in evenly for us. And we're running out of a little space, so we'll kind of go over here. So we have 1/9, and then 45, and then 54 divided by 3 end up giving us, looks like 1/18, looks like 18. And we can add inside that parenthesis, we'll have a 1/9 and 63, which will give us a final result of 7. And this is a production rate of cars per, in this case, hour. Cars per hour. So that would be our average value of this rate function. So this would be an average hourly production rate. We can notice that over that whole 9-hour interval, we produced 63 cars. So that just the interval itself gave us the total number of cars produced during those 9 hours. And when we divided by 9, we got that average hourly rate. The last thing we'll do is just to consider how this would apply to just a graph of a function. If we wanted to find the average value of the function over a given interval just using graph properties, let's go ahead and consider the average value for the interval 1 to 4 on our function. So this function, again, its average value, f average, could be described as 1 divided by 4 minus 1 times the integral from 1 to 4 of our function. Now the integral itself, again, is just going to be the area trapped below the curve from 1 to 4. So let's go ahead and try finding that first. From 1 all the way to 4 will be that section of the graph. Each of these boxes is one area, 1 unit of area. So we got 1, 2, 3, 4, 5 units of area plus a half here. So we have 5.5 units of area, or we could call that 11 halves units of area. So 5.5 or 11 halves would be equivalent there. So in this average value, it looks like we have a 1/3 on the outside, and then that integral itself, again, will just be 5 halves or 11, or 5.5 and 11 halves for our area. So that average value comes out to 11 divided by 6, or just under 2. So if we were to kind of draw that in, let's just see where that would place us. The average value would be 11 over 6, so somewhere kind of right in here. If we were to kind of level out that area, we'd have 11 over 6 for that one. All right, we can take a look at the second interval here to finish up, and I'll leave some of these values on because they'll be helpful for us. In this second one, we will consider the interval from 2 to 6. So f average for us is going to be, again, from the interval 6 minus 2, integral from 2 to 6 of the same function. So let's just see what the area, again, would produce for that integral from 2 all the way to 6. Again, we can consider what's the area that's trapped below the curve from 2 to 6. Well, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9.5 units of area here. And if we convert that to a improper fraction, looks like that would give us 19 halves, be the equivalent. So we can take our interval of 4 units, so 1 over 4, times the total area there, which is 19 over 2, and that gives us an average value, 19 over 6. Or over 8, excuse me, over 8. There we go. That looks better. 19 over 8. Or just to get a feel for this number, looks like 2 3/8. So almost 2.5 would be our average value there. And that would be the complete work there. So we've got 2 average values over those intervals, just using the properties of our graph. So in this video, again, we looked at the area between 2 curves and also the concept of the average value, again, the average y value of a function using integrals and integral properties. So thanks for watching this lesson. Feel free to take a look at the examples again throughout this video, and I'll see you guys in the next video.